Hello, everybody. Back in Algebra 1, when you guys studied linear functions, and you looked at the slope of the line, we interpret that as a average rate of change. And I want to talk about that a little more tonight. So imagine that you have a situation where your dog might have a tumor, you might have a tumor, and you go to the doctor and you say, originally at t equals 0, they size your tumor and they find it to be 0.5 cubic centimeters. And a week later, you go in, it's grown to 1 cubic centimeter. 2 weeks later, it's grown to 1.5, and 3 weeks later, it's grown to 2 cubic centimeters. So if we plot all those points out on an axis here, so let's say this is 0.5. Let's do these. Yeah, let's say this one here is like 0.5. Let's say this is going to be 1. That's 1.5, and let's say that's 2. Illustrate here. Okay. So that, at t equals 0, the size of the tumor is that. If we call this the volume, cubic centimeters. And let's just make this our time in weeks, t. So this is plotting out the data here, right? So at 0, you're at 0.5. 1 week later, let's say this is week 1. You've grown to 1 cubic centimeter. In 2 weeks, 1.5 cubic centimeters. At 3 weeks, you're at 2. Basically, we get a nice straight line out of this, and kind of illustrate that here. So this line sort of represents volume based on time. So if I give you a time value, you should be able to maybe come up with even the equation of that line and be able to tell me, after 10 weeks, what do you think the volume is going to be? But you can see by looking at the pattern here too, right? As you look at how fast is it going every week? What's the rate of change of this tumor? What's its growth rate? Right? I mean, if we take the slope and pick any pair of points, it don't matter which pair you pick. Maybe I pick those two there. Do that in red. Okay. Red. There we go. Like that point, maybe in that point, right? If I compute the rise over the run, right, 2 minus 1 is 1. That's my rise. And if I look at the run, I got to take 3 minus 1 here, which is 2. Right, so we got 1 over 2. My slope is 1/2, or 0.5. And you kind of knew that. It was going up by 0.5. What were the units again? Oh, notice that the y values are in cubic centimeters. And the run units with time was in weeks here, right? Weeks. And we kind of assumed that the growth rate of that tumor is growing at about that speed, right? At about 0.5 cubic centimeters per week. In fact, we could have probably predicted that. If I asked you, what do you think it would be in week 4, based on how the data looks, right? You'd probably tell me, I think most of you would tell me it would be at about 2.5, wouldn't you say? Because that's how fast it's growing every week, right? That many cubic centimeters per week. So in this sense, the rate of change in this case represents the speed in which how fast the tumor grows. Okay. If we go back and we look at the units from the linear regression equation for Felix Baumgartner skydive from the stratosphere, right, what did the slope represent in that case? If you recall, he was so many meters above the Earth, and the time units were in seconds, right? So whatever his slope was, the number here was the numeric value, but the units were in meters per second. If I'm talking about miles per hour, or kilometers per hour, or now even meters per second, right? That's a distance versus time unit. That's speed, right? So basically, we're saying the slope represented his average speed in that case. Now, cancer, people falling out of the sky, they don't fall at the same rate and they don't grow at the same rate, right? So what do you think the graph should look like if cancer were to go untreated? Make up some numbers that you think would be better represent the cancer tumor's growth and connect points. Find the slope between 4 different points and explain your answer. So I don't know, let's say I go in, and I'm guessing at t equals 0 here. Let's see, I'm going to say my tumor growth is maybe, we'll start even with the 0.5 like we did last time. This time I think after a week or so, week going into it, I'm going to say it's about a 0.8. I'm going to say after 2 weeks it's going to be at about let's say a point, so I make it a 0.9, and in 30 weeks I make it a 1.1. Okay. Is that what I wanted? Not really. I want to change those numbers. I have a feeling like if I just draw the graph, it would probably look something like this. Or it could even look like something like this. But it's not going to be some straight line because cancer doesn't grow at the same rate all the time. In fact, it's probably going to get to a certain level, and that's probably going to be all you can handle at that point. So I'm going to stick with the red one, my guess. Okay, so maybe at t equals 0, this here right here would be like 0.5. Maybe after a week into it, this has grown to 2. After 2 weeks into it, it's grown to 4. And after 3 weeks, it's grown to, let's say this up here is equal to 5. Okay, 5. So if this was the case, then we're going to look at the slope. How do we find the slope? It's not a line, right? It's a curve. And that's the whole point. If you got a curve, what we can do is pick out a pair of points on that curve, say this point and this point, and we can connect those points with a line. And just as what we did before, right? Finding the slope of the line represents the average rate of change. Picking 2 arbitrary points on a function and calculating the slope of the line that joins those points is how we're going to handle it with functions that are not linear. So if we look at the rise over run of the purple line now, we're going to have 5 minus 2, which is 3 cubic centimeters per. And if I look at the bottom there, I got 3 minus 1, which is 2. So 3 over 2 is 1.5. So if I was to come in, I was the doctor, and maybe, someone shows up in my office and they say, okay, after a week, I looked at your tumor, it was 2 cubic centimeters. I missed a week. I came back 3 weeks later, or 2 weeks later from them, and I found out, oh, it was 5 cubic centimeters. I'm going to think that your tumor is growing on an average of about 1.5 cubic centimeters per week. Excuse me. Okay. Now, if I picked a different pair of points, maybe I chose at this point here after 2 weeks, which is in green, and I picked the third week here, which is in green also now. I connect those with the line. Right, my growth rate won't be as intense, right? It looks like it's actually smoothing out a little bit. Okay. So the green line, if we compute its slope, right, we're going to have 5 minus 4 for the rise, which is 1. And my run is now 3 minus 2, which is 1. So if I look at the slope of the line going through those green points, I'm just going to get 1 cubic centimeter per week. Okay. And similarly, I can do this with other points, right? I can maybe pick one more, maybe in red. Say I pick the initial value of the size of the tumor, 0.5. This is the volume in cubic centimeters, right? This is your time again in weeks. Okay, but if I pick the first initial point, 0.5, and then maybe I pick the, I don't know, maybe this point here again. And let's look at the first and last points and compute those slopes. Then you can see from there, your rise distance now is going to go all the way from there to there, which is going to be 5 minus 0.5. That's 4.5. Okay. And the run would be 3 minus 0, right? Because we're at 0 right there. So that's going to be 3. So over the whole, I guess, 3-week period from when you started going to the doc, I think it's even giving a different slope value, which is 4.5 is the rise and the run is 3. Okay. Now, 4.5, if we divide that by 3, what is that here? Let's see, 4.5. I'm feeling lazy today, 4.5. Let's divide that by 3. It's 1.5 again. Cubic centimeters per week. All right, so depending upon which weeks I look at, I might, not really know how fast this tumor is really growing, right? Because I'm doing this over a period of time. What I'd like to know how to find out is how do I find the speed in which that tumor grows right now at this moment. When we get into the derivatives later, we will discuss that.